Okay, so that actually it was a good accident because you spend time trying to think what's going to happen, right? And then it's not on the record. So now let me see. First thing first, this is the mistakes that especially senior who still here. They always do this in a sense because when you look at this, the only way that this can deform is this, right? You can't have your structure deform otherwise. It's like you put your ruler on a bend it down. The only way you can bend is by having a negative curvature. You can't bend it positively because the rigid point is there. That's where the support is. Correct? So invariably, it means like, you know, exactly what's going to happen is that generally you should have negative moment at the substance. You can't have positive moment and you can't have zero moment unless it's here, what we call the end support, the support at the end. If it's the end support and it's a hinge or roller, the moment is zero. Yes. So you can guesstimate sort of this has to be negative moment because your structure cannot deform otherwise. And the fact that if you have a long enough beam and you have the load pushing it downward like this, you should have the deflected shape that looks like that. Correct? And here it also should look like this. Because of the hinge and the roller at the end, it has to come down immediately. Can't be any other way. It has to come down. But this also has to come down like that because here is the rigid zone. Here is the rigid zone. Meaning, exaggerate this a little bit. Generally, your structure would be like this. And again, point of inflection, where the curvature changes. So you would expect, before you even do it, that your structure would have this positive moment diagram, but here, because of the only way you can deform is that, so you better have a negative. Before you even do it, you can sketch your bending moment diagram. It can't be far away from a shape like this. Right? This is from trust your feeling, Luke, something like that kind of moment. Right? Become a Jedi master by talk to the structure. Because the only way that you can have the deflected shape is this. And if you can't imagine your deflected shape, this is the corresponding bending moment diagram. So instead of hitting everything head on and okay, I now get my bending moment diagram, I can sketch my deflected shape. You can sort of predict what the deflected shape is going to look like and anticipate what kind of bending moment diagram you should have. Okay? One day you guys are gonna work on the structure, okay? And we probably don't do detailed calculations like these anymore. But the fact that you can predict the behavior of the structure to understand what's going to happen will help you a great deal. And you can ask your junior, hey, go and give, find me some homework, okay? But you can expect what the numbers that they're going to give you. That's why I have one problem in the midterm, number one, to ask to find what's wrong with the calculations. That's what you are expected to be able to do. Yeah. Okay. All right. So if you have time, we're going to come back and then try to solve this one. But now let's move on to see this one. Okay. I like that, right? It's a frame, indeterminate frame. And you see, you have plenty of choices as for your primary structure. But let's say first thing first, you have 4 reactions. Don't mind the directions, okay? We have 4 reactions. So we have 3 equilibrium equations. So first, step number 1, degree of redundancy is, we now know it's 1 degree of redundancy. You can remove many things, but you can remove either one of them of the reaction. But I myself would prefer to remove the horizontal one. Some would try to remove the vertical reaction. And now you end up having something like this. Yeah, I guess it's still stable, but it's going to be something that you are not completely familiar with. Right? So please don't be so, say, unpredictable at times. You know, say, I'm going to do this. Why not? Yeah, why not? But can you get it right? Right. For example, this one. Let me go back for a minute. Say here, this one. We have 3 choices to turn this into a primary structure. First one I already did. I removed the roller. The second one, as some of your friends have said last time, you can also do this. Right? And now you calculate the rotation step. The third one is by doing this. Remove the moment and now have something called, this is a fixed support, but no vertical reaction. It's called shear release. You release the shear. Yes, you can do this. But the question is, can you? I mean, you can, this can be your choice. This can be your alternative. Can you carry it out? So it's a choice you make. You can make your life easier, or you can make your life extremely uncomfortable by doing something like this. Not. I have seen students do this, but I have never seen anyone complete it. 100% correct. You know. Okay, so I would suggest you do something not far away from your comfort zone, because you don't need to show me how hard you can, solve the problem. I just want you to solve the problem. You don't need to show me, hey, I'm pretty good. I can, do crazy things just to show you better than you. No, it's not about that. It's about something else. Okay, so I would say I remove the horizontal reaction, and I would step number 2, my primary structure. I prefer to remove. Let's give it some names. A, B, C. So primary structure. I'd say I remove HD. Okay. So now I have structure that looks like this. Looks kind of friendly enough. So and if you really want to practice, you can go back home and try to remove maybe HA and match my answer. just for fun. Okay, you can do this, and then you can pick up, because I have given you so many exercises, right? You can do it with your friends. Try, okay, I'm gonna remove this and I'm gonna remove that. See if you can, in the end, get the same answers. It's a good practice, and it would be much more fun if somebody would get something wrong. Because by trying to find what is wrong with your calculation, you will also learn something, and you can prevent that from ever happening again in the future when you know your mistakes. It's not a bad thing, don't you? To make mistakes while you still can. That's why we practice, because that will be the time that allow you to make all kinds of mistakes, so that you won't make another when you're not supposed to. Okay, so here we go. Um, Here is my primary structure, and here, because I remember carefully, because I remove HT, so I will have horizontal displacement at D. And because I have horizontal displacement at D, it means I need to apply my unit at D. So let's make it like this. And you see, for some of your friends who still struggle to analyze a structure like this, you don't have to talk about how they can write Boolean equations, right? If they struggle to solve the frame like this, there's no need to write Boolean equations. If you get the wrong reaction, everything else will be a mess. So from here, let me say, I will not go into details about the calculation of the reactions, okay? You're supposed to be able to do it. So here is 20. That has to be 20 for sure. Oh, reactions that use a different color. That's 20. And now, because at the moment that is 4, what's the unit? Kilonewton per meter. You take the moment at A, you should get this reaction. Be careful, you take the moment at A. Okay, everything goes in the same direction. So it's 20 multiplied by 15. This is that. So this reaction should be greater than another one. Remember, find it yourself. Okay. That's the first case. In the second case, the probably most common mistake that you will make is that this is the reaction, right? It's one equal opposite, but they do not coincide. So you must have another reaction to balance out of the structure. Some of you who have done the exercise in the last Thursday, when you face the frame that looks like that and you apply the unit, this is easy because your reactions are concentric. This, so you don't have anything else. You don't have the vertical reactions, but here you do, because these two forces here and here, they do not pass the same line, which we use the word concentric or coincide. No, they do not coincide. They are not concentric. So you have to have the vertical reactions to help balance the moment caused by this couple, right? And because they are 30 meters this direction and 30 meters here, that's why your reaction comes out to be same because of the same momentum. Okay. Again, we seem to have an issue with the point load. See, when you see the point load, what you see is the disruption of your moment diagram. And if you can see quickly your moment diagram here, that's 20, right? So your moment here is going to go up 20 multiplied by 15. So that's 300, right? Very quickly. See, no calculation. Just you can just sketch, because if you are looking from here, this load goes up, so it's positive moment. And then look at this. Now the two loads are the same. So it means that after this, the shear force is 0. Am I correct? Yeah. Or you can, if you don't see it, you can try to draw your free body diagram. 20, 50, 20. So shear here has to be 0, right? Meaning the moment here just the consequence of this attack. So it has to be constant, because your shear is 0, so your moment is constant, right? See, I'm not doing anything new. It's a good old knowledge of free body diagram, equilibrium, and calculus. Zero shear, constant point. Yeah. So we can draw the diagram very quickly, because now you know your shear is 0. Your shear force diagram is just this, right? It's right. How many seconds? Maybe less than 5. What time? It's supposed to be professional in less than 2 years, right? To be able to do it. So now you know that is again disruption here at this point. So you need 2 moment equations. So again, you have to choose what's going to happen with your moment equations. Would you keep your x from here? Because when you look at this, your moment diagram, that is one equation, right? If you keep your x from here, you don't have to change this equation, because you can just keep your x from here. But if you want to start your x new with a constant here, you're going to have to come up with the new equations for the virtual load case. Okay, and now another portion, it's a CD, right? And then, you know, if you want to write your moment from, let's use another color. If you want to write your moment from here, you know you have a moment constant, because you have a moment there. Here must be negative moment, right? And here is 1 multiplied by 30. That is 30. So if you want to write your moment equation, you must have it. I mean, from the left, you must have the moment. So why don't we try to write from the right? It's much more comfortable, right? Makes more sense. So I'm not going to write from left to right. I'm just going to write from right to left. Just gives me a clean free end begin with. So something, a choice like this, you know, comes down to experience, which you gain from practice. Okay. So, any question before we dive into yet another series of calculations? I guess none. I'll try to squeeze everything in this page so that you can see the moment equation with this free body diagram. Okay. So let's say step number 3 and 4. We are going to calculate the displacement, right? So right now I have my portion. Now I have my big moment, AB. No. Okay. So the AB is this portion, correct? This is where you don't have to make a choice just yet. So your moment is 20x, and your small moment now is x. Actually, try to use this to make the moment here is also possible. That you don't go crazy. It's possible. Okay. And range is from 0 to 50. I thought it was cold in the beginning. Now I sweat. Now, portion BC. After this external 20 kilonewton of load, okay, BC. Now, I kind of prefer to keep one equation if I can use it throughout. So if I'm going to use my small x equal small moment equal to x here, but in this case it doesn't matter because it becomes a constant, right? So you can say from 0 to 15, you have to change it, right? But it's constant or the actual case, so And okay, you guys are ready? Make some notes. So let's catch a breath a little bit. Now from DC. Question? Maybe ask me. I'm not gonna eat you. Because I have to cook you first, right? All right. So if you get from B to C, that would give us 70x minus 4x squared over 2, right? Yep. You can see that without having to draw the free body diagram anymore. Let's look at this piece, right? 70x pushing up, so it's a positive moment, and this uniform load pushing it down, so it's a negative moment. For those of you who may need this moment BC coming from this free body diagram, right? We begin from here. This is 70. We take the moment there, mx, and then we have the uniform load. That's exactly what you always need to do before, right? But in this class, we sort of skip that. And let me move this a little bit. Okay. And in the virtual load case or the unit load case, we have the luxury of having the same equation again. Now it's from 0 to 30. Now, don't get confused again. When we calculate displacement due to the actual load, we multiply this together, right? And when we calculate the displacement due to the unit load, the unit load becomes both the actual and virtual load. That's why we can square them. So for those of you who participated in active session, just about 30 of you, you would get the better picture there. Sort of, give you a better, say, oh, Eric, really scary. Scared shitty. Something is going to go wrong again, and you're going to have to call the night. Could you please come here? There's something bad happens again because I touched it. Okay, so Now it's just the calculation. Okay. Here is when you are you open the door to the calculation by using mathematics because you can apply your engineering knowledge. Okay. Without proper engineering knowledge, you will not come this far. And now it's just calculus. Delta D now is big M multiplied by small m, right? So it's from 0 to 15, 20x multiplied by x, dx over di. Second portion, 15, 30. Be careful. If you want to use from 0 to 15, you have to change the small m, right? This equation valid from 15 to 30. If you somehow change the range to 0 to 15 and you use x, it means that you are now using the moment equation in portion AB, right? Can't do that. Here is 300 multiplied by x, dx over di, and the last portion, 0 to 30. Here is 70x minus 2x squared and x over. So I'm not going to go through this. You can use your calculator, correct? So the answer is 3, 4, 8, 7, 5, 0. Over a lot of number, big number. But it doesn't mean that your final reflection come out huge. It depends on your DI, right? DI can be huge. Now I hope that some of you who were a little bit confused last week about the actual virtual unit, something like that, they can get a clear picture today. Okay. Now now this is when the actual and the virtual are identical. So we can just go ahead and you see that's a benefit of having the same equation. I suffer the range, but when it comes to the integration of the virtual load, I can just wrap it up 0 to 30 x and x dx over ei. Can you see that? Because it's the same equation, I can add the range. Right? They have the same equation, so I can just use that little law of calculation of calculus. Right? You can add the boundary and form 0 to 30 instead. Instead of doing 0 to 15 plus 15 to 30, you can use 0 to 30 boundary. Guess what? It's just exactly the same for DC. So I can multiply that by 2 as well, right? Because they just happen to be the same. So I can multiply that by 2. And without further ado, I'll give you the answer. 18,000 over the they were discussing heavily in the classroom. So I'm just waiting for them in case they may wanna just let me into their world. Maybe they don't just get away from me. That kind of stuff. Right? I want to suffer by myself. Don't talk to me, instructor. Get away from me. I've had enough of you. Right? No questions, maybe? Crystal clear? Really? It's like this. Wow, revelation. Like that? Maybe? Okay. Anyway. So, remember that before you do heavy calculations, just get the concept right. Because I think, as I said before, and you guys were laughing, that sometimes we spend too much time worrying about the calculation itself, whether or not we get it correctly. But what you put in your calculation is the best. So you can't calculate garbage, expect it to come out good. So you must make sure that when everything comes to this point, it's all correct. Okay, and I believe that I give more points on the development than here. Here is still something, but yeah, if you, I think let's go back. Here you see that indeterminate frame, that's part of our exam. You see, primary structure alone will give you 20%. Proper moment equation with corrected. This is 50%, but I give the percentage on the correction of the calculation, maybe just 10%. So if you can establish something correctly, but you somehow fail to carry out your calculus, you get probably 50 or 60% already. But you have to get the right moment equations. Okay, otherwise, what are we talking about compatibility and solve compatibility stuff when you can't write moment equations? Focus here. You don't have to take it for this information is given to you right at the beginning of the class. Okay, let us come back here. Oh, not that. Yes. Okay. So now, if you come this far, you can write your compatibility. Okay. Now it is delta D plus delta DD multiplied by HG equal to 0. So now we have 3, 4, 8, 7, 5, 0, 3 bar 9 plus 18,000 over 9 multiplied by HG equal to 0. So yes, here we go again. HG is negative 19.375 kilonewton, which means that if my HD is in fact the opposite direction of the unit load that I apply. You're free to scroll back up, but you don't need to because I'm just going to redraw it. Now I have this. Watch superposition at its best. This is your first case. 20. 4 kilonewton per meter. Now you have your reaction here is 50, 20, 70, right? And another you remember the first time we applied this, right? And we got this. So our result is negative. So it means that this is in fact in this direction. And it's 19.375, right? Some of you still are making notes. So I'm just waiting for you because I want you to see this with me without looking somewhere else. Ready? There's some of you still take notes. I'll wait. Please don't draw flowers or birds, trees, and say, "Oh, I'm not done yet." Trying to demonstrate the fact that you're writing something, but you draw flowers. So, did you guys see the eclipse last night? Neither did I. I forgot. I was cooking the dinner for my family. Once in a while, I do that because my wife just came back from somewhere and she looked a little bit sick. So I wanted to do this because I didn't think that she would come back early. So I had a one menu. I wanted to try cooking for my kids. Just wanted to see how it worked. Didn't turn out to look the way I wished, but everybody said it was yummy. Put it down. And I missed my mark, but it turned out okay. Guys who this is on the record. Generally, guys who drink cookware. I stopped drinking for 20 years now, but I used to drink, so I tend to cookware. And some of my friends who just drink very heavily. You know why? Say because we've got a thick tongue. We drink a lot, we can't taste anything anymore, so we tend to put a lot of ingredients into our cooking, so it makes the taste very strong. But it doesn't always work. But let's say it's all the record. Okay, let's come back. Here, the real reaction is opposite. So if now is 1 to the right, and our real reaction is 19 to the left. This is 1 to the right, so the real one is 19 to the left, right? Remember, everything is linear. So you can multiply everything here by 19.375, right? Or minus 19.375. So you know right away that this is the real reaction due to the fact that you have it. And here it now upward 19.375. Here is now downward 19.375. Because you solve it, now you know. If everything was 1, this is your all your reactions, right? If everything was 1. So now if HD was 19.375, you can multiply everything without ever having to calculate it again, right? Do you believe in elastic? And if you believe in superposition, you can add them up. Why? Because most students who are afraid of superposition, after you get this, you will go back, apply this, and calculate the reactions again. Right? With me, what? iPad would like to share something. So, may I decline that? Okay. Okay. Maybe I'll accept that later. So now I have my system, the true system. with this and that, 20 and that. Notice that I now have the two hinges, right? Notice that I have two hinges now on the latest drawing because I have add the second case. This is the case where I now have the reaction, right? Here. So I add this with this. This roller becomes a hinge here. And I now have the reaction here. This, I can just add them up, right? This is 50 plus 19,375. This is 20 minus 19.375. Yes? This, oops, sorry, why did I do that? Sorry. Where did it come from? Yeah, right. And but you didn't tell me. You just let me do it. To embarrass me, right? There, right? So here is 70 minus 90.375. And here there's nothing. So it's 19.375. So you're done with the reaction, just like that. Bear with me for a minute. I want to finish the shear force and bending moment diagram. Okay? So let's show you this for a moment. Because some students will just like this very much, you know. Some just gonna take that reaction. But if you're not convinced, you know, try it. Try it on your sides, right? Try doing this. See if it matches your home. If it does, why bother? This is much quicker, right? So okay. Now this is probably just 0.05. This is 69.375. This turns out to be 50.625. No. Please don't draw flowers, guys. Ready? I am right, right? When I'm joking, you draw flowers. You draw flowers. I do. Maybe. Okay. So let's do this quickly. The first piece now, we have 2.6 going up. You meet with the reactions, you meet with the external load. So that's your shear force diagram. Okay. Which is force minus 19.375. This is 0.025. And the shear in this direction, this is upward, so actually down, and here is 69.375 comes down to, this is 50, right? So 69 is larger than 50. So you try to draw this to give yourself the upper area bigger than the lower area, to give you some idea that okay, you actually have the larger positive area than the negative one. Your proper drawing will help you a great deal. Okay. And now bending moment diagram. You know, some of you come this far, still you don't believe in your equilibrium. This is the positive area, so you have positive moment here, and the area is equal to just 9.4. And this negative area should bring your moment diagram down to the moment at the joint, which is no, 9.4 is from 0.625 multiplied by 15, right? So this point is 9.4 minus 19.375 multiplied by 15, right? Use the shear force area. And it is equal to minus 281.2. And that's what you should match, even if you, but if you, you can draw this bending moment diagram from right to left, but it must be pretty good. Because right here in the negative shear, it should bring the positive moment back down to 0. So this negative area should give you positive value here. Right? Here is 12.66. And the moment should come down and match with this number. Okay. 281, and here is positive moment is 320. Okay. Any questions? Let's wrap this up here for break. Questions, please. Friends, you write something frantically. Frantically. Know what I mean? No? Frantic, like that. No, again, how many do we have here? 12. Online is about 30, give or take. So we have half the students in attendance. Whatever happens to the one who never show up? Either way, they're the ones going to fail. And sometimes, we're trying very hard to help you if we are concerned that you haven't done the term well, then nobody shows up. Right? Okay. If we don't have any questions, let me stop the video. It just goes long.